All right, vector fields and Desmos, a probably not very great combination, but I'm going to try making this work anyways. I am doing a very impromptu video here, explaining what's going on in this graph I made on Desmos. Probably like the fourth time I've done something like this, but this is the first time I'm going to document it online. Does something this simple need a video? Probably not, but it doesn't hurt. I can post almost anything onto YouTube as long as it's PG, and this thing is this is about as PG as it gets, as long as you're not rendering this onto a sphere. So I'm going to just do a quick rundown of everything you see here. This is as you would see it if you load up the link that I'm going to give. So let's go through the basic controls here, and then we can go into the nitty-gritty of how this works. So up here we have two functions. These are the two functions of our vector field. A lot of people would probably want to represent a vector field with a matrix or vectors. You can't in Desmos. It's an unfortunate thing. There's a matrix calculator, but it's not for graphing. So we have to do it in two functions here for 2 dimensions. And this is a very simple one right here. And this is a solution to it. This is not a part of the graph, but just a simple solution to see, this is basically just what you'd see when you load it up. And this is one of the main uses of vector fields, is to create graphs like this. This is a parametric function, and it generates an ellipse given this starting vector, this starting position. All right, and add a couple of fun features here. So first, we can shrink or grow these vectors. Pretty important, because if you set it to 1, this is the actual length of the vectors, and not nice. So I'm going to shrink these all down to very measly, what is this? That's a pretty good length for this size. We can't render the entire screen. That would be a lot. Right here we have 400 vectors. Rendering all of it is not something for the most computers, or actually I think this is computed over the web, but regardless, not a good idea. Next here is the number of vectors that we'll get. It's the frequency. So that's pretty self-explanatory. It's not zooming in and out, even though it kind of looks like it. This is actually changing the number of vectors you see in case you want to zoom in more or less. Set this back to 2. And I mislabeled it says A of width. It's J. W. W sets the number of vectors. So if we increase it, we get more vectors. Decrease it, get less vectors. So that's probably good. Here's some advanced controls here. You can skip all this. It's not really that important because it's pretty self-explanatory. So if we do interpolate here, they're not all unit vectors. How fun. This is, this can be pretty important. And if you're using this tool to create slope fields, kind of necessary. All right, and we could set all to black in case you're not a fan of rainbow. And to be clear, this rainbow is not preset to be radial. The color represents the length of the vectors to make it a bit easier to see, but if it's not easier to see, you can set to black. Inverting also makes it easier to see, but it's literally inversion of the screen. So let's see what's next. The hue. Here we go. This sets how fast, the frequency of the hue angle given the length of the vectors. So if you do something like this, we kind of get into some aliasing there. But something like this, it's kind of random, but if we set it down here, you can actually see it pretty good, and it looks kind of nice. And you can set the starting angle of the hue. We set it to play, it gets a rainbow effect. All right, last 2. If we move it over to the right, it moves over to the right, and so on. This is just in case, depending on which part of the graph you're looking at, you don't want to waste resources if you only want to look in one quadrant. All right, if you skipped, this is where you should have skipped to, because now we're actually going to look at the nitty-gritty details. All of what you see right here, this is all of the vector field. So what you'll notice here is that this is five variable declarations, or declaration would be more appropriate in this case, though I guess technically not, and 1 graph. this is our graph right here. It's all of the vectors and, wait for it, that's not all of it. So this is the actual graphing part. Over here, this is setting the range and domain. That literally takes up twice the screen. So how fun. I'm sure there's ways this could actually be simplified, but I don't know. I didn't see any immediately, though there might probably be a couple. You could shorten all this by doing some abstractions. And I'm going to start by explaining this function here, and then we can get into what all these other things down here do. So when I move over to this tab, it's the same thing. However, it is the same thing, except I changed the vector field a little bit. It's now 1/3 to make it a little easier for us to see, and I hid the vector field. All right, so the first task in this is to draw a vector. That's the most basic thing here. You know, it's kind of a programming approach to how you would solve this problem. So if you have a point here, and wow, frame rate's nice when it's nothing's on the screen. So if we have this point here, and we have the vector field up here, the definitions, and we want to draw the vector here, we're going to start by finding the end point of the vector. So if we assume the green point is the starting of the vector, the green is the end of the vector. This is simple, and if you're making this, you know, properly in some software like, I don't know, OpenGL, this is about as far as you need to go with the math, because you just draw a line between those 2 points. But we aren't drawing a line between these 2 points. There's multiple ways you can do that. I'm 99% sure Desmos can do that, but, you know, where's the fun in just making Desmos do it? I don't even know what the line function is, but I know it exists. It probably exists. All right, so next step is to create the line between these 2 points. Basic algebra. There we go. So remember, green is the start point, and that's the line in between them. And what we want to do is cut out everything that's not between the 2 lines. And there's many ways to do it, and the way I'm going to do it is by setting the range and domain. That's why it looks so massive, is because, you know, setting the range and domain is a little bit tricky, because you can't say, you know, set a function to be between 2 points. That's not actually an option when you're setting range and domain. Well, it might be, but for Desmos, it's not. You have to just do an inequality. For example, x, and this is the notation that Desmos uses. X, let's say we want to be between 0 greater than x. Nope, that is the wrong symbol. Greater than 1. There you go. That's the basic way of defining the range, and it's between -1 and 1. However, if we swap these two around, nothing happens. It doesn't work, because now nothing could ever satisfy this inequality. You know, what number is what was it? What number would be greater than 1 and less than -1? There are no numbers like that. Probably. Not in Desmos, at least. All right. And so how are we going to set the balance between them? So so this is the function here. And we're going to look inside. This is not the problem solving technique. You don't just look at the final solution. But we're going to pull things out of this final solution. I'm going to explain each part of it to you. So you're going to see throughout this entire thing a very common repeated function, that is the sign of either the f function or the g function plus 1/2, or the negative version minus 1/2. So what is going on here? So the sign function, let's hide up this. The sign function, not sin, sign. I think it also stands for some Latin word. So sign function, sine of x. This is an incredibly simple function. I mean, if it's less than 0, it's -1. If it's greater than 0, it's +1. 0 is 0. This is nearly equal to x divided by divided by absolute value of x. Nearly the same, except at 0, where it doesn't equal anything. And if you don't believe in the sine function, because you didn't learn that in school, you can just use that mostly. Though having 0 equals 0 is kind of important. And what's special about this function? Well, if you want something to be a negative number in one case and a positive number in a different case, you can use this function simply by multiplying your function by this and whatever the condition is to set the sign. But we have another thing we can do with this. What if we want this be between 0 and 1? All right, well, pretty simple. Plus 1. Now it's between 0 and 2. And how we get, what number is going to make 2 equal 1? Well, we just divide it by 2. There we go. Now it's between 0 and 1. And now 0 actually equals 0.5, but I just think it's significant, but I don't care too much about that. And I very recently found out this is called a step function. I didn't know. I discovered this on my own, like sometime in high school, and had no idea anybody else discovered it, which is kind of obvious. People would discover this, but never heard people talk about it because it's not the kind of thing you see in a calculus or algebra class, because that's a little funky. So what's special about this? Well, it kind of turns other functions on and off. Given different conditions. X is the condition. So if we want it to be, off at 4, 4 minus, so it's on, so it's equals 1 all the way up till 4, and it equals 0. And that's important because we can say multiply this by x. Now it's going to equal x everywhere that's less than 4. Pretty simple. This is kind of analogous to an if greater than, if less than statement in programming languages. I guess this would probably be a qualifier to make basic algebra Turing complete, though that's not really a shocker whatsoever. All right, so we're gonna look down here, and I am going to sample. Let's see. I'm gonna sample this right here. I'm fumbling a little bit. Sorry. Actually, this is over here. So I'm just going to take this straight from the formula I made. All right, and what's going on here? We see 2 of these step functions, my version of the step function. And I'm going to remove some stuff. I'm going to ignore this. I'm going to replace it with x2. Move this one, y1. Get rid of the f. Move x and x. That is everything. All right. And now it's identical to that one down there. All right, so what's going on here? In this function, you can see it's not between 0 and 1. It is still step-like. So what does that mean? I have forgotten to define these. I defined these as something else. Sorry. All right. So what is this doing? Well, if I move this down, you see what's doing already. It's setting it to be between x2 and y2. This is what this function does very simply. All right, and now what's going to happen if I just reverse their signs? Or I guess I'm not reversing their signs, but the sign of negative x is equal to negative sign of x. So sign with a G. So what we do here, it's flipped around along the axis. So simple, right? So when x is less than 0, we're going to have the purple function on the bottom and the blue function on top. And on the other side, it's going to be the opposite, blue on bottom, purple on top. All right, and why is this special? Well, remember, with the inequalities, we can't just, say between 2 points. If we could just say blue is on top always, purple's always on bottom. But we can't do that. At some point, we have to say, swap them around in a different condition. So, and our condition is x. If x is below a certain number, purple is on bottom, purple is the smaller number. Otherwise, blue is the smaller number. All right, so how can we use this up here? I'm going to bring this back. Oops, wrong. I actually made a tangent line. All right, here we go. So remember, starting point right there. Oh, not that relevant. So I'm going to take this function. What am I going to do? I'm going to say x is f of x1, y1. And what is the second one? It's also going to be f of x1, y1. And very simple. We're almost there. This gives us a value that is equal, the value. So this means that if this means that if f of x1, y1 is less than 0, then x1 will be, sorry, I'm going to get this a little flipped around. X1 should be, x2 will be what we should get the value of x2. And if f of x1, y1 is positive, we will get the value y2. All right, and we're going to just set it to x equals that. And oopsies, did I do something wrong? I did. I didn't set x2 and y2. So when we're going to set x2 to, it should be x1. Right? And y2 should be x1 plus f of x1, y1. There we go. That's the black point. All right, and delete this just again. There we go. We got the left bound and the right bound. All right. So remember, this y2 is the position that the end of the vector is at, and y2. Oh, sorry, this is very impromptu. Y2 is equal to the endpoint, the x coordinate of the endpoint, and x2 is the starting point. And here's what we're going to notice. I'm going to move this around. Watch carefully. Oops. Oh, yep, that is correct. I'm so sorry. It's a little hard to see. You're going to notice something. Purple is always on the right. Always on the right. We're always going to have purple on the right. All right, so now the inequality will hold true. All right, I haven't tested this out yet, so let's hope I don't mess up. So I'm going to quickly do this. And something left. Less than x less than. Oops. So I got the there, that should be it. Yep, that is it. Great. There we go. Got a basic vector. It goes around between the two endpoints. You're gonna wonder, it looked a little bit more complicated than this. What's going on here? This is not equivalent to all of this. All right, well, first of all, remember I put in a feature that said the vector could be any length. And the vector length here is, you can see this is very simple. It's the endpoint. We said the endpoint was f of x, x1, y1 plus x1. And here you see it's been divided by something. What's going on there? So why is it divided by 1? That's the same thing. Well, if you look up here, I divided it by q1. And what's q1? Q1 is a variable that determines the length of each vector. So that's what's going on over there. I'm going to move along over here, and oopsies, what is this? What is this function? All right, let's talk about what that is, because this solves a pretty big bug. If the vector is perfectly perpendicular, and I'm sorry, I don't think I can make it perfectly perpendicular like that without doing some algebra, so sorry. You have to take my word. If the vector is perfectly perpendicular, it won't show, because now the bounds are now overlapping. And even though if you say that they're equal to each other, if you didn't use less than, you use less than equal than, Desmos just doesn't really get it. So in a perfect world, you don't need all the extra things I did. But Desmos is a little finicky. So we're going to create a situation where if the vector is perfectly vertical, ignore all the bound stuff, all right? Let the vector just be its vector, and we'll use a different bounds function, a different inequality to define the start and end point vertically. All right, so that's what we're doing here. So let's look. What is this here? Well, we've got a square in here. What on earth is the square doing here? Well, I'm gonna change this with x, and can you already see what's going on up there? Remove some of this. Here we go. Well, it just looks like 0, right? Well, you see that little gray point right there? In the situation that x equals 0, it's 1. Otherwise, it's 0. That's what this function is doing here. Now, the square part, it has nothing to do with like the properties of squares or anything. We're just looking at a u-shaped function where it equals 0 at one point and is positive everywhere else. That's all we're doing here. This could very easily be absolute value of x. Exact same thing. All right, we're just using x squared because, why not? Use xx, whatever. All right, it's 1 minus because otherwise it's actually 0. It's actually 1 everywhere except that 0. 1 minus. So this says if in the situation that f of x1, y1 is 0, do nothing. Because if f of x1, y1 is 0, that means you have a vertical vector or no vector. But if there's no vector, then who cares? We don't want to render it anyways. So that's why we have this conditional here. We've said all of this. However, in a situation where it's vertical, just add 1. All right. And over here, it is going to subtract 1. If I am remembering everything I did correctly, because I made this a little bit ago, I made all of this like in a class period, like half a class period when I should have been paying attention. And then I realized later, well, I should probably, make it so it can have vertical vectors, and I dragged my feet on that. All right, so over here, this is literally just the same thing on the left, but we swapped it with g of x1, y1, which remember is the y equivalent, and also swapped it with the y1 factor. So there we go. So I've turned this on. Just, here we go. That function will render any vector we give it, as long as it exists, So that is so fun. All right, so now you're wondering, this is not too crazy, is it? It looks crazy, but theoretically not that crazy. You're probably wondering, how am I making, 400 vectors with one function and a bunch of variables? Well, it's a thing that Desmos lets you do. So in Desmos, if you can create a table, it's a list, I don't know what they call it. So let's say, I don't know, r, I haven't used that variable, r equals square bracket, 0, 1, 5, 9, 8, 9, whatever. And oopsies, r means something, r1, there you go. So now we have a 5-element list. This is very computer science. You even use the square brackets, but whatever. I guess not computer science, programming. It's very programming because we're using square brackets, and this doesn't even have matrices. Matrices don't exist to this. So this is our closest thing to matrices. All right. So, and it also has a special thing you can do. 0, 1, dot, 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 10. 11 element list. It's made we've given it a pattern. It's a linear, it's making a list. It goes from 0, 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. That's our 11 element list. Well, I guess we don't have to do 0, 1. We could do 0, 1. There we go. It's 101 element. Do it. Pi, 32 elements, whatever. And the special thing is, what happens when we try to use this as a variable? Well, let's see. X, and you can predict what happens. R1. We now have 32 lines right here. How fun. This is pretty powerful when you want to do things like this in Desmos. But now you're probably wondering, how on earth did we manage to put it in a square shape? If you know how an analog television works, then it might actually seem pretty easy. Not easy, obvious. It seems pretty obvious if you know how analog television works, CRT. So we have a one-dimensional list, a one-dimensional array. Can we get it to 2 dimensions? Well, not really. You can't make r into r squared. That's not really a thing as far as I'm aware. Maybe it is, but probably not. But we can kind of fake it. In this case, we don't need a continuum. We have discrete values here. So we're going to say is, values on the list from 0 to 10, you're part of the first row. From 11 to 20, you're part of the second row, so on and so forth. And how are we going to do that? Well, back to the vector field. Right here, we define our list. This is actually the only thing on here that we have to define outside. Actually, do we have to? We don't technically have to define any of these outside this function here, but I'm defining them outside because it makes it really ugly, and I think would tank performance really badly. Yeah, probably. I assume Desmos is well programmed to do pre-computing. Maybe not, but none of this technically has to be outside, but we're putting this outside, make it easier to use. So L is a list from it's just all the natural numbers between 0 and w squared minus 1. Remember, w squared, that's the width. The width squared minus 1. So how do we transform that? Well, think about it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or in this case, it's going to be w. So, yeah. So 0 through all the way up to w, first row, we simply set the x-coordinate of each of those points to the value of it. Just so, if we want to translate, index 0 to the 0 to the first point, we just have to set the x value to its index. So index 0, x value 0. Index 2, not index, wrong terms. This is really, sorry. So 1 would go to x value 1, 2 to 2, 3 to x value 3, all the way up to 10, and then what do we do on 11? We can't say it's 11 because we defined the bound to be, you define it to be of width w. So at 11, we wrap back over to 0. I may be off by 1 there, but whatever. And what function do we do that with? Well, the modulo, a favorite of mine. What does the modulo do? It gives you the remainder of 2. When you divide two things, it gives you the remainder. Something that you've probably not thought of since elementary school. What the remainder, the remainder of division. What's that? Who cares? You calculated this division anyways. Well, this gives you the remainder. And more practically, it loops over and over. So you start on 0 and move all the way up, back to 0, all the way up, back to 0, bump, bump, bump. And that's what this is doing here. You see the modulo right there? In a lot of programming languages, it's the percent sign, but in Desmos, it's the modulo. And I think there's, I think there's other notation for it too, but just mod L to the width. So L here is the index, so it's going through every point, and what it's doing here is when you set a variable to an expression, and one of the variables is a list. That means that you've created a new list. It says right there, 400 element list. Now, I should clarify one thing right here. If you put 2 different lists in there, you're not going to get it enumerating through one of them and then the next one. It's not going to double nest them like a double nested loop in a programming language. It's going to enumerate through all of them at once. So it's going to go through first. So if you have list F, and if you have list F and then list G, it's going to go from F of 1, G of 1, and this guy, the next one's going to be F of 2, G of 2, and then so on until both of them are out. So this is why I have to do it, in case you're wondering, why don't we just have 2? You have to do it this way, because this is not a programming language. I guess technically it is, but it doesn't have the luxuries of a lot of programming languages. So A here is the x value. We go up here. Oops, there we go. That's the x value. F of x1? No, it's f of a. This is the x value here. It's a list. All right. Delete that. All right. So now how do we get the y value? Well, you could just use the its index already. It's going to get you something kind of there. But if you want it to be square shaped, have right angles, we have to floor it to use the floor function. In programming, the modulo and the floor programming, oh my god, the modulo function and the floor function are actually very nice because they work very well with bitwise operations. And I suspect this is probably why television has worked so well. If this wonderful part of the universe didn't exist, television might struggle to exist too. Though I guess it's not digital; it is analog. But we have computers interface with them up until the LCD and LED and so on and so on. But that's not that important. So if you haven't followed along with what I'm saying, I'm just going to show you. I'm going to just display every point. So this is every point in the list AB. There we go. That's our square. You can see, what am I trying to do right here? Yes. Lines. Turn off the points here. It's basically just reading like a book or like a scan line on a CRT. You're just going over, and then once you hit the edge, go over to the next one, over, next one. In this case, it's going the opposite direction of the direction a CRT goes, to the direction that you read. But I mean, you can go the other way. I don't know. Negative. Yeah, there we go. Now it's in the direction. Now it goes in the direction that you read, or the way the television scans. All right. And do that. All right. So we set the x value, that's a, and the y value here is b. So we plug those in there, and then you see we do have x and y in there because that's necessary for graphing. Because we're still living in the xy plane right now. So I'm gonna turn this on. There we go. All right. That's nearly all there is to explain. Let's just do a little bit more. Color. This is the fancy new. It's not that new. It's new-ish. Newish function in Desmos. It's a custom function called HSV. You're probably not going to find this in any math textbook. This is a computer graphics thing. No, it's a bit more than computer graphics. It's computer literacy. HSV is hue saturation value. There's also RGB. I think there might be CMYK. I don't think so. If we look in here, we should probably see it. These are all the things that they have. Oop, there we go. See, there's polygon. You could probably just have to draw lines. There we go, RGB and HSV. No CMYK. Sorry. Though you could invert it. Oh, now we have CMYK. That's not worth getting into. So, what am I doing here? So, the color, if you remember, is based on the color is based on the magnitude. So the hue here, this is what makes it colorful, is equal to the magnitude of the vector. Remember, this is a list. Colors can be lists. This is a very cool thing. A lot of things can be lists in Desmos. Colors are actually one of them. And when you set a color, you can go into the settings up here and just set it to that custom color you made, and it will work as a list, just as a variable in itself. In fact, there's other things you can edit in here, such as the line opacity. If it's 1, actually you can't see it, it's 0. 0.5. You could set that to a variable. So now it's, I don't know why you'd want to do that, but why you'd want to do it that way, but you can totally set it as a variable. Same with the line thickness. You can't set this, but I don't know. And the color. This can all be controlled by variables. It's a very nice thing that it lets do. And I'm pretty sure it's pretty new. So the HSV right here, and this is set in color. The hue is, so the hue is the magnitude multiplied by A of hue. Remember, that's the frequency that we go through this in. HSV is, it's got some relationship to waves, because I'm not going to get into it. It has relationship to waves, so this is the frequency here, plus the shift. So this is kind of like a sine function, I guess, maybe. And the saturation here is 1 minus black. So in a situation where black is equal to 1, saturation is 0. It means it's all grayed out. And in the situation where it is 0, where black is 0, then it results in 1, which means very colorful, the maximum color, unnaturally colorful. Really, you're not going to find any color like that in nature, but this isn't nature. All right, and over here, it's pretty much the exact same thing for the color. So if it's set to black, it is black. There you go. All right, and the last thing is the vector lengths. So you look down here. There's basic control, because you're gonna want to control this regularly. You can set the length of the vectors. Of course, 1 is the accurate length, but you don't do that when you render vector fields. So you can set the length, but remember this interpolate. If we set interpolate 0, they're all unit vectors. What's with that? Well, sort of unit vectors. What's going on over here? Well, let's go right back up here. This is Q1. Look up here. That's the length of the vectors. So in the situation where interpolate equals 0, we're going to have this function right here. This function is going to be shrink here. It's going to be 1 over shrink times the magnitude. What that results in? A unit vector, a scaled unit vector. And over here, we multiply that by 1 minus interpolate. So this is the interpolation function, the linear interpolation function. And you could have used the linear interpolation function to do all of this. It's my favorite function. You could have done it to do all of this here, but I didn't because, I don't know, felt like it's wrong. I don't know. I'm not going to talk about the interpolation function. This works because it works. That's all that matters. You can kind of just look at it and think about it long enough and it makes sense. All right. That is it, actually. So I can go back to what you should see when you load this up. And there you go. And you can, do whatever you want. Set the square. And this is, well, now this is inaccurate. Set the square, this is square root y, whatever. Do whatever you want with it. Who cares? This is not the best one out there. This is probably not the best one out there. But I made it, so whatever, and I can show it online because I can. This video was way too long. I'm not going to trim it down at all. Very sorry. You did not have to watch this. Maybe you shouldn't have. Whatever. Have a nice day.